Hi, and welcome again to my Physics Online video lecture series. In today's video, I'm going to be wrapping up this series on energy with a little discussion of the topic or concept of power. So, at this point, we have discussed things such as work and energy and the work kinetic energy theorem and the conservation of energy and the concept of mechanical energy. Everything kind of points back to this definition for work, that work is force dotted with displacement, or in other words is the x component of force times the x displacement plus the y component of force times the y displacement. Whoops. Actually, it is a scalar, so these vector terms can go away. We've also defined some terms such as kinetic energy, translational, which is 1/2 mv squared. We've defined a variety of potential energies. We have looked at graphs of force versus displacement and obtained work and energy from those graphs. So today we come to the next point, which is, suppose that I have a set of stairs. So there's just like a bunch of steps, and I have some people who are going to climb those stairs. Apparently my stairs have become a ramp. I have some people who want to climb the stairs. And there's different ways that you can climb stairs. You can take them one step at a time, slowly, or if you're in a hurry you might run up them one step at a time, but like step more quickly, or you might go 2 steps at a time, etc. In any case, I think that we've all, if we've climbed stairs both quickly and slowly, notice that there is a difference between walking up a flight of stairs and running up the same flight. At the top of the flight that we've run up, we often feel a little bit more winded than the flight that we've walked up. And the question should arise in many of your minds as to why that would be. After all, if I take this right here to be the u equals 0 level, then this is u equals mgh, where these stairs have a total height h, and this is the same number in both cases. mgh is the same number in both cases. It means that work is the same whether we walk or run. And I should qualify that statement by saying it's more or less the same. Obviously you have a different amount of, let's say, drag that you have to work against, like air resistance. So obviously it's not the exact same, but it's to within a reasonable approximation. If you've climbed many stairs, you've done the same amount of work whether you walked up them, whether you ran up them, or whether you went up 2 steps at a time, or what have you. But it doesn't seem to take the same amount of effort in both cases. Okay, another case in point. If you've ever lifted weights, not everybody does, but if you have, or if you've watched somebody lifting weights, you've got this kind of weight on the ground that you're going to try to pick up, and when you lift it, you can either lift it quickly or slowly. I've apparently made the bar really thick, but you can try to lift the weight up fairly quickly or fairly slowly, and in either case, as long as you've done the same motion, you've done the same amount of work. So from the side, maybe the weight has gone from on the ground to 3/4 of a meter above the ground, let's say, like so. So we got our guy trying to lift it here, and then he's straightened up over here and is holding the weight. Okay, well, in whether this process is done quickly or slowly, the weight has moved through the same distance. It's moved through, let's say, 3/4 of a meter, and it is the same amount of weight. So this person should have done the same amount of work whether this was done very quickly or very slowly. Now, you may, for let's say a relatively lightweight, maybe you're doing a warm-up round of, I don't know, maybe instead of deadlifts, maybe you're doing like rows or something like that. And so you're just kind of like lifting it off the ground and then setting it down. So maybe this thing has a total weight of, let's say, 40 kilograms, right? And so you row the thing off the ground, and it's pretty light, so you do a bunch of rows in rapid succession. That gets your heart rate going very quickly. And yet, if you've done the same number of lifts or rows, repetitions, whatever you want to say, and taken 3 times longer to do them because you're lifting very slowly and steadily, your heart may or may not rise by all that much. So what is the difference in these situations? Why does speed matter? Well, we have a new concept that we can introduce today, which is power. And power is basically the rate at which work is done or energy is delivered to a system. So power is rate of work, or rate of energy change, if you prefer. So if you were to write an equation for power, P is defined by work over time, or if you prefer, delta E over delta T. And as with so many other things, this definition is really like an average for our general physics course, for our college-based, algebra-based physics course. If you want to get an instantaneous value for power, look at how much work is being done in a very, very short amount of time. And so divide the work by the time. Alternatively, if you want to plot work or energy versus time, so let's say here's time and here's work, and maybe you have a plot like this, then the power at this moment in time must be the slope of the tangent line. So this is, let's say, T0 or T interest or whatever. So slope of tangent gives you power. Slope of tangent equals power, instantaneous. So at time T0. And then conversely, that also means that if instead I have a plot of power versus time, power delivered and time, like this, that if I take the area between 2 points, let's call this T1 and T2, that this area in here is equal to work done by system, or on system, from T1 to T2, so during that time interval. Okay, so that defines power. So now let's go back to these conceptual examples. I've got this guy lifting a weight, or I've got this guy climbing the stairs. What is different if you run up the stairs or if you quickly lift the weight than if you walk up the stairs or slowly lift the weight? Well, it takes more time to walk upstairs than to run upstairs, and it takes more time to very slowly draw the weight upward than to quickly pull it upward. So given that power is work per unit time, work over time, if I have a longer amount of time to do the same work, in other words, W remains the same but T gets bigger, then the power is going to be smaller, and vice versa. Before we go to the examples, let's note that the power actually has units associated with it. So what are the units for power? The common unit for MKS, the one that you'll mostly be working with, is the watt. So watts, which uses a capital W, not to be confused with work. 1 watt is equal to 1 joule of power, one joule of work per second. There's a second commonly used one. Well, there's two other commonly used ones. There's the feet, pound, seconds version, but the other commonly used one, also from the imperial system, is the horsepower. Now, 1 horsepower is approximately equal to 746 watts. 745.6999 watts for what it's worth, but roughly 746 watts. So with that in mind, let's go ahead and do a quick example to close today's video. How much power is needed to lift a 100 kilogram weight by 0.75 meters in 2 seconds? So in other words, we're doing these deadlifts with roughly 220 or so pounds. So your power should be equal to the work divided by the time. And the work should be m times g times delta h. In other words, it's the change in potential energy divided by the time. So you have a mass of 100 kilograms. You have g, which is 9.8 meters per second squared. You have 0.75 meters, and you're doing all that in 2 seconds. You can place that all into your calculator. That gives us a total power of about 367.5. So let's call that 368 watts. If we divide that by 746, we get 0.492, so roughly 0.49 horsepower. Put differently, if you can pull this 100 kilograms, a complete deadlift in 1 second, then you're generating almost, though not quite, 1 horsepower. That's all for today's video. I hope you've learned something from it, and thanks for watching.